Good morning, everyone. Good morning, family. I hope this video finds you all healthy and hale. It means you're feeling well. Today's date is May 26th, 2020. It is 9:18 in the morning. I just got off the morning meeting, and now I'm doing the greetings, salutations, and we're going to combine it with the word of the day. Sorry, I'm tired. It was Memorial Day weekend, and I was just up at night. My tooth is killing me. Nothing, up at night didn't mean I was partying. The exact opposite. I have a pretty solid toothache, and I couldn't sleep last night. So, anyways, I hope all of you are doing well. I'm going to read today, give you a couple of words to ponder and ruminate upon. Ruminate means to think, to cogitate also means to think. Ruminate also is a way of describing how animals digest leafy products and grass. Ruminants are a multi-stomach quadruped, means animals with four legs. We're bipedal, we have 2 feet. Quadruped, quadrus, four feet. Quadrupedal ruminants are animals like goats, cows, anything that chews grass that has 3, sometimes even 4 stomachs to extract the nutrients out of grass and provide energy for the cells in the muscles of those animals. But anyways, they're called ruminants because they chew cud, which is another statement. Anyways, you can look all that stuff up. You don't have to wait for me to tell you. Nope, not answering, but I will reply. Can't talk now. What's up? On my cell phone. Sorry about that. I got it under my desk. So last time we did the adjustables. Today we'll talk about advanced mechanism. It's an interesting concept. I'll read it first and then we'll talk about it. A device used to trigger an earlier spark based on engine conditions. Originally, advanced mechanism was based on vacuum. I'll tell you how that will work. Now, with computers running everything, the spark table, and it's literally, interestingly enough, we were just talking about Excel spreadsheets. The newer spark tables is basically a glorified spreadsheet that the computer reads based upon several factors. It's a 3D map. It's really interesting, actually. It's based on RPM, at how many revolutions per minute the engine is currently spinning. It's based on throttle position. The computer takes into account how far down you've got that pedal mashed, or throttle position or input. It's also based on engine load. Whether or not, whether or not the engine's working hard or being asked to work hard. Modern cars also take into account things as bizarre as automobile altitude, how high up in the air it is. It's very important to know. It's important to know mass airflow, which is probably the way the car finds out its altitude if it does not using an altimeter. It's based on what else can the computer see? Third yawn in a row. I'm very tired. But I'm up and we're doing it, so yay. I'm sure I'm missing things that the ECU can see that instruct the vehicle in either advancing timing or retarding timing, which are genuine uh, mechanical terms that you guys are going to have to be familiar with. So let's talk a little bit about how an engine works, how an internal combustion engine works. So we all know that it needs air to breathe. We all know we need fuel to burn. We all know that the motor needs a way of igniting the mixture, the spark, through igniting the spark plug using electricity. We all know it needs compression. Otherwise, it's basically just throwing a match on a puddle of gasoline. It just sits there and flutters. So you need to be able to compress it. It's got to be hot, so it can't be super cold in order for an engine to operate properly. It has to be in the right temperature range. So it's not just the combustion triangle. There's a lot of things that go into making a car, an internal combustion engine, work properly. We also need lubrication to ensure we don't have a premature detonation. We need to have coolant running properly to ensure that the engine doesn't melt down. I know those things are all not part of what you have to get a combustion event, but they are all absolutely critical in the continued multi-cylinder firing of a combustion engine. So we talked about timing. So there's several different types of timing. Well, it's only one type of timing, but that type of timing can be applied to several different places. All timed combustion events are based on the piston's position within the block, in its sleeve, in its cylinder bore, either at or approaching bottom dead center, which is the deepest part of the engine stroke, or at top dead center, where the piston's at its topmost position of spark. Now, in your mind's eye, if you can remember seeing how that crankshaft spins around based on the pistons going up like pedals on a bike, and as your foot gets to its topmost position on the pedal, that's when the valves are closed, and you either have a combustion event or you've just squeezed all of the exhaust gases out. It can only be one or the other at top dead center. It's either the exhaust valves are open and all the spent gases are being pushed out, or your valves are closed and it's a compression. It's at the end of the compression event where that piston has risen up into the top of the chamber and it's squeezed all of its air fuel mixture into that super compressed volatile mix. And at that particular moment, we will say the advanced mechanism will tell the computer, now's the time to ignite the air fuel mixture at idle, because that's its best position. It takes into account how fast the ignition process takes, and it takes into account how fast the flame front propagates. Propagates is just a way of saying how fast it moves from the center where you've lit it. You'll notice, and a fast and easy way to talk about propagation is if in your lives you've ever, I'll put it this way, you've ever seen a video rather than doing in real life. Because I don't want you doing it in real life. Seen a video of someone who has made a line of gunpowder, of a wick for a firecracker, or poured a line of gasoline out. And you take your lighter and you light one end. The speed that the flame takes as it goes across whatever you're lighting, you can even have a row of crushed up pieces of paper. It will have an incredibly slow propagation rate. How fast that flame propagates, how fast it moves along that line of poured out gasoline, along that line of poured out gunpowder, along that line of a wick for a stick of dynamite, like in the movies where you get the big wick of dynamite and you light it and he's holding the stick of dynamite. That propagation rate, the speed with which that flame, that sparkly flame, moves along the wick or the line of gunpowder or the line of gasoline is called propagation. Now you'll notice that I even included when you've poured out gasoline, you can actually measure the speed of the propagation rate of gasoline, and it's measured in feet per second, FPS. So the propagation rate for gasoline poured out is different. It's slower than the propagation rate of atomized fuel. Atomized fuel burns a little bit quicker, as opposed to the flame front just rolling along the top, the boundary layer of poured gasoline. Because remember, gasoline itself is not igniting. The gasoline is a liquid which stays unlit. The flame on poured out gasoline you've put in a cup and poured out, or even just have a cup of gasoline. If I have a cup of gas and I take a lighter and I light the gas, the only thing that catches fire is not the liquid gasoline below, but where the gasoline meets the air. Remember, you need air to breathe. So the gasoline, as the fumes come off the top of the gasoline, the fumes of evaporating gasoline interact and mix with the air and become a combustible or flammable mixture. So you're basically lighting the gasoline fumes as it's mixing with the air. Now, in open air, air reaches stoichiometric or stoichiometry naturally. It uses whatever amount of air it needs to combust. And this is because we have different varying lengths of flame. Part of the flame starts near the boundary layer, and the rest of the flame takes in oxygen along the length of the heat column of heat. That's why it's hotter to have your guys. Remember when we were using the oxyacetylene? And I had that sucker, it was blasting out like my finger, and you could put your hand all around it, and the boundary layer between the oxyacetylene torch blue flame was jetting out. So there was always a constant cooling air flow coming up behind it and pushing out the front where the flame front was being directed, right? So you can put your hands to the sides of the flame and it wouldn't be anything. But if you went in front of the flame, hot, right? It would be super hot. Well, gasoline operates, but because it's not compressed, all it does is heat goes up, so the flame front goes up. It's the only reason why flames go up, because that column of hot air draws up. Because in a gravity environment that's unpressurized, heavy cold things go down, hot light things go up. And it's that natural up-down movement that draws air up into the heat column, giving flames a vertical appearance. In microgravity or in 0G, if you take a drop of gasoline and you put it in the air, it looks like this marble, this clear marble, that like gelatinous ball, and you can light it, and the whole surface of the globe of gasoline floating in the air starts to burn at the boundary layer. Heat doesn't go up in space. Heat radiates out. There's no up and down in space. It's really cool. There's videos. And you might say to yourself, Mr. Romer, why are you talking about all this? I said, well, it lays the foundation of knowledge you need so that when I start describing advanced mechanism, you'll go, oh, that's why. I go, right. So we now have established that you're at least reminding yourself of the top dead center and bottom dead center concepts as it relates to where the piston is. We've established that we're thinking about valves opening and closing. And we're also thinking about the use of the spark plug to ignite the the air and atomized fuel mixture present in the combustion chamber, the combustion event of a 4-cycle gasoline cylinder engine. So where does advanced mechanism, and why is there advanced mechanism? I'll describe that too. So here we go. Back in the 1800s, as they're all trying to figure out how to make gasoline engines work, they use carburetors, right? Carburetor sucks in air, and by Venturi effect, it also pulls in just the right amount of fuel. How does it? I'm not going to go into that now. Just trust me that the old-timey cars use carburetors, and the carburetors would have air getting sucked through them, and it was being sucked through, they had these little tubes called jets, and the jets, as the air goes past, would have, by Venturi effect, fuel pulled into the jet stream. And that was how old-timey cars had their fuel metered in. They had metering jets. Be that as it may. So now we have a piston filled with fuel, right? It's just sitting there. We have to turn the crank to open up the valve to let in the air. Because remember, when we turn the crank, we also turn the connecting chain that rotates the two or one camshaft, which tell the valves when to open and close. So as we rotate the crankshaft, the piston comes down, sucks in the air-fuel mixture until it's filled when the piston's at bottom dead center, and hopefully somewhere near the bottom, as the crankshaft keeps turning and the piston is at bottom dead center and starts to head back up again, the valves close, sealing up the piston. Now the piston's squishing it back up, all the way to it, like, watch my elbow, right? Top dead center, it's pushed all the way up, and it's at maximum squish. That piston is squeezed. The air-fuel mixture inside of that piston, inside that cylinder, to its maximum amount. And you would think, well, Mr. Romer, the best time to light that amount of air-fuel mixed is right there at maximum squish. And I would say, when you're just starting a car, it is. Right then and there, at top dead center, that is the optimal time to ignite that air-fuel mixture for maximum efficiency and maximum amount of power for the amount of air and fuel inside the cylinder. And as the ignition event occurs, as you let the electricity flow at that instant, from modern day cars, we use igniters. Old-timey cars use distributor caps going through a coil. It would let that electricity released on that ignition wire, which was attached to the spark plug, and the spark plug would spark, and the ignition would occur in the cylinder, and you'd have a combustion event. And that flame would burn, and that heat would want to expand, and that expanding gas air mixture, it's like a cloud in there. As it expanded, it would push the cylinder down, and we'd get power. Now here comes the interesting part. There is a speed to the spark plug igniting and that flame front. Remember, we were talking about propagation? There is a speed with which air-fuel mixture propagates out through the air-fuel mixture inside the cylinder. There's a speed. There's a start time and a stop time. Now, it's milliseconds, but it's there. And it's the same every time. It's the speed with which flames move through the fuel and air mixture. You can clock it. It's got a speed on it, like 2 or 3 milliseconds. Knowing this, here comes like, well, Mr. Romer, why do we have retarded or advanced ignition events? Why isn't it just every time it gets to top dead center, you ignite that mixture and you get power? And at idle, absolutely. As close as you can get it to top dead center, ignite it, and off it goes. The difference, though, comes up when the engine's running really well and we're putting a lot of gasoline in. Okay? You put a lot of gasoline in, it takes a little more time for all of the gasoline to be ignited because there's more to ignite, right? Not a lot, a millisecond. That's all we're talking. Milliseconds. Hundreds of thousands of a second. Slices of a second. Super small sections of time. But here's the thing. Even super small lengths of time, when a car's at idle, that piston isn't moving very far in a millisecond. But at 8,000-9,000 RPMs, you better believe that piston is moving up and down super quickly. As a matter of fact, in 10 milliseconds, a piston can go from its 9/10 compression point up to 10/10 and back down to 7/10 compression, all in several milliseconds. At idle, 1 millisecond, the piston will just be in one location. But at 9,000 RPM, as that piston's flying up and down, 1 millisecond will take you from almost top dead center to all the way maybe half an inch down. That's huge. So here's where these concepts all come together. Imagine, you will, at the front of your crankshaft, as your first piston, the very first one in the row, or the number one piston, is at top dead center with its connecting rod standing perfectly vertical, connected to the crankshaft, whose bearing surface point, that where the connecting rod attaches to the crankshaft, that round part right there, it grabs onto. You can see the connecting rod come down and grab onto it. That bearing surface is also stood up at its most perfect 12 o'clock position, right? Everything is standing at its topmost position. If you took a pizza plate, a pizza pan, you go to the pizza parlor, right? And you get pizza and it comes out on that big silver plate. If you took that plate down and you put it on your tabletop and you started to make lines, you made one line down the middle, made one line across left to right, and then you start sectioning off like slices of a pizza to make all the lines like spokes on a wheel radiate out, you would be able to dissect and bisect that pizza wheel into 360 slices. That's a lot of thin little slices. But each slice is 1 degree. We all know a circle has 360 degrees. 1/4 of a circle is 90 degrees. 1/2 of a circle is 180. 3/4 of a circle is 270. And a full circle is, right, 360 degrees. Okay? So what we're doing is, when we're timing our combustion events, we have to be aware of how many degrees the crankshaft has turned in relation to top dead center, which is the best location to start a combustion event when the engine is not yet running. Okay? So you take the plate with 0 being perfectly up, and you take a nut and a bolt, and you bolt the pizza plate onto the crankshaft, and you see 0, and you go, okay, to start the car, top dead center with both valves closed is 0 degrees on my crankshaft. Now remember, interestingly enough, we all remember that the crankshaft turns around twice. It goes through 2 separate rotations, or 720 degrees of rotation for 1 combustion event. Suck, squish, bang, blow, right? So from top dead center, 0 degrees, to bottom dead center, first rotation, to the bottom is 180 degrees. That just is 1 piston traveling down. Now from 180 degrees to back up to the top, the piston goes back up. It is just done 1/2 of a combustion event. It's either, at that point, had its valves, the intake valve open, so now it's sucking in, it's pulling like if you're on a straw and you're pulling the air-fuel mixture in at 180. The valves will close, and now the piston will, on its from 180 through 270 back up to 0 again, be squishing that air-fuel mixture up. Now, at the top of this, if the air and fuel have been sucked in and the valves are closed, if we ignite that mixture at its topmost point, it'll give us our first ignition event, which will then push down on the piston, connecting rod, bearing, journal bearing surface, and push that crankshaft down like you're pushing down on your first push on a pedal on a bike. It's really hard. But you're pushing from the very, very top. Who here's ever been on a bike where the chain is connected directly to the rear sprocket and you can't rest your feet? You always have to pedal. Have you ever been to a point where the pedals are moving so fast that your feet come off because you can't pedal that quick and the pedals are spinning? This is where the concept of, well, at least in my mind, how I'm describing to you how advanced mechanisms work and why. At a certain point, as the piston's going around and around faster and faster, through 2,000 RPM, through 5,000 RPM, through 8,000 RPM, there comes a point when the piston is moving so quick that as the piston goes up to squish everything inside the cylinder, if the spark plug would go off right then and the flame would start to propagate out through the air-fuel mixture, atomized fuel and air mixed up in the top of that piston, the genuine piston speed of the engine spinning would be faster than the air-fuel mixture expanding. So what would happen is the piston would already be flying down and the flame front's trying to play catch up to come down through all the mixture to cause it to expand. And so the faster you rev an engine, the more you need to advance the timing event before top dead center. Now I want you guys to wrap your head around that. As the valve, right, so we got air fuel coming in, pistons going down. It's at bottom dead center. We're at 180 degrees on the first rotation of our timing wheel. Now the piston's starting to come up, so that's 180 through 270 degrees. That's halfway up, approaching 360 or 0 again, which is approaching top dead center as the crankshaft is spinning, as the piston, remember, it's all in motion, as the piston's getting nearer and nearer to top dead center, coming nearer and nearer to maximum squish. Now, when the engine's just starting off, it doesn't matter. You ignite that spark right at the top. But in an engine that's running at 8,000, 9,000, 10,000 RPM, if you light it right at top dead center, the flame front is chasing the piston and it provides no power. So you go, well, how do we make it provide power? And engineers went, we ignite it before top dead center, in advance of TDC, top dead center. So we need to have it occur. Now, the general rule of thumb is usually try to set an engine for around 10 degrees before top dead center. You'll hear him talk about 10 degrees, TDC. That's a starting point for a decent engine. That's running a couple thousand RPM, 0 to 5,000 RPM, 10 degrees top dead center is fine. So what that means is if our crankshaft is advanced or before the ignition event, 10 degrees. That's not a lot. It's a little bit of a rotation of our crank. If you remember that pizza wheel. So we go 10 degrees before top dead center or 350 degrees on the wheel. If we time our ignition event for 10 degrees before top dead center, as the piston's flying at 10,000 RPM, the flame starts. We're going to have our ignition event happen there. It will allow the flame, because remember, the piston's going up and down, not the whole engine. So the piston's going up and down. The thing that's rotating is the crankshaft. So as the crankshaft is nearing top dead center, it gets to 350 degrees before 360 or 0, top dead center. As that pizza wheel with the markings comes up to 350 degrees, the ignition event occurs there. And through that, we get to see that as the ignition event occurs, the flame front will be moving through the air-fuel mixture as the last movement of the piston provides just enough compression so that somewhere right at or slightly 1 or 2 degrees after, the flame front has now propagated its way through all the fuel air mixture so that right at TDC or just a hair after. That's fine. That's, in engineering terms, it's perfect, right? Right at or right after, that flame has now gone and used up all the air fuel and the maximum amount of pressure has been created. And so now it will push with force and speed the piston back down. So the piston, you're still squeezing as it approaches 10 degrees before top dead center, and it squeezes up and then blasts it down. And that's good. I shouldn't say 10,000 RPM. Let's say 5,000 RPM. 10 degrees is good for 5,000 RPM in like a V8. Idling to 5,000. When you're talking about much higher RPMs, you want to advance the timing even more. Because now I should have used a motorcycle, because then we can do, 0 to 0, 5 degrees at 5,000, 10 degrees at 10,000. And at 15,000 RPM, because it's a Suzuki GSXR 600RR, it revs to 20 grand. Ding, 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 right? So, and it's just the same in cars. It's just scaled up, scaled down. At 15,000 RPM, those pistons are hauling tuchus up and down really fast, like a sewing machine, right? And so when you have the pistons moving up that fast, up and down that fast, you want to increase the advance on how soon that spark occurs so that when the piston finally gets up to top dead center, it's at maximum squish where the flame front's pretty much used up all its air fuel and you've reached maximum pressure. Because that's what we really want in a piston is pressure. We've used up all the air fuel, we've burned it all, it's at maximum pressure. But because the piston's moving so quick, we have to start it even sooner on its way up. And so we take a look at the degree wheel and we go, well, 10 degrees before top dead center was pretty good. But because the piston's moving even faster now, if we started at 10 degrees before top dead center, that piston will squish and the flame's not done burning yet, and it'll go back down, and the flame's still burning, trying to catch up. We even have to advance it more. So now we're talking like 15 degrees. In reality, I'm just using these numbers to get you guys familiar with the concept. But in reality, you can dial in on an inline 4-cylinder well-balanced engine or a 6-cylinder well-balanced engine with small, well, it doesn't matter about the size of the pistons. I'm just saying a nice, decent 2JZ. You can be talking 28 degrees advance at 7,500 RPM. We're talking 30 degrees on the wheel. 30 degrees brings you to 270. 28 degrees is here, right before 270 degrees. There's 30 degrees of advanced ignition timing. So as the crankshaft's spinning and the degree wheel's turning with it, if the computer sees 280 degrees, it goes, ignite now! And it sends the signal to the spark plug to ignite, and the piston's on its way up. And all of a sudden, you've got an ignition event. As the fuel burns, the piston's coming up. It's coming up. It's squishing for maximum pressure, right? And then that air-fuel mixture is compressed and hot and can push the piston down. And that's awesome. So one or two of you smart kids out there will go, well, Mr. Romer, why don't we just have it ignite right when the air and the fuel get in the cylinder? And that way, as the piston goes around the bottom and squishes it closed, it will get maximum amount of push. And it has to do with flame front and fuel exhaustion. So if you ignite the air-fuel mixture too much too soon, where all of the air-fuel mixture has been burned and is waiting for the piston to come back up, that fuel front moving through the fuel actually has concussive force. That flame front is strong. And if your piston is moving up and the flame is moving down, and if the two meet before the flame front is done, you end up with the flame front smacking into the piston, wanting to push down as the flame front meets. And you end up with a pre-ignition event where the majority of the pressure is meeting the upward moving piston. And at this point, that pre-ignition event is now pushing on your piston, not wanting to let it come up. It is such a strong event that it creates a knocking sound inside the cylinder. That flame front smacks up onto the top of the piston and makes a noise like taking a hammer and hitting the top of the piston. Alloy pistons will actually ping. Ding, ding, ding. It actually makes a pinging noise. Cast iron sounds like a knock, and that's where you get the word knock. Knock is a pre-ignition event, an untimed, or if you've set the timing wrong, an event where the air-fuel mixture ignited too soon and met an upcoming piston and tried to stop its upward travel. We're not trying to stop the travel. We're trying to time the event so that as the flame's propagating, the piston squishes it and it gets its maximum amount of burn as it's compressing into its last amount. As long as it's still burning, we're allowed, we can, that energy point can be compressed a little bit. There's sponginess to that event. But if the air fuel mixture is already ignited and burnt and sitting there in pressure, that pressure wave will smack down into the piston, causing knock. Premature ignition event. So, engineers have to be super careful in this timing event. You can't just dial in 60 degrees and let it fly. No, you're going to pre-det the whole thing. It's got to be perfect, where just the right amount of the fuel-air mixture has started to burn, and it's at how many pounds, or it's actually, there's CPUs, copper pressure units. It's the amount of force necessary to compress 1 inch of copper. I've got research to do to find out the copper pressure of unit analogy, but just know that it takes how much pressure it takes to squish down 1 piece of copper. That's what the force is. But think about that. There's so much force, you can squish copper, right? So at a certain point, at 49,000 CPUs, the amount of pressure built up in a cylinder is too much and it blows out your head gasket, or, blows out the side of your block. Engines are built to withstand X amount of tens of thousands of CPU copper units of pressure. How much that is, I don't know off the top of my head as I sit here on a Tuesday morning in COVID-19. I can remember a lot of things, guys. CPU units. It's like 49,000. I'll be close. I might not be right, but I'll be close to give you an idea. So what happens is you want to be able to start the burn and the combust this fuel air mixture before top dead center, or just a little bit out. You want to make it so that all the fuel gets burned at or a little bit after top dead center for maximum pushback down on the piston top. You want to start the event advanced of 000 or 360 of the degree wheel. So sometime before it, you want to do that. If the engine runs to 15,000 RPM, you really need to start that ignition event way early, 28 degrees early, so that when the flame front, because that piston's moving super fast, so it clears that distance really quickly and is able to achieve most efficient combustion. All the fuel's burned as it reaches top dead center and pushing back down. Pre-ignition event is when that air fuel mixture is lit off and completely burned through prior to the piston being anywhere near top dead center. And then the piston wants to get pushed back down the way it was coming as it's coming up. That flame front meets it. The pressure front meets it. And it goes bing if it's alloy, or it knocks. So you say, okay, Mr. Roma, we got it. We got flame fronts. We understand that the faster the piston moves up and down means the faster the RPMs. And if we were just lighting the match, igniting that mixture using the spark plug at 0 degrees top dead center as the crankshaft's spinning and the piston's coming up and down, that the flame front would chase the piston. So we want to start the flame. We want to initiate or start the ignition process before top dead center. So we start it in advance of top dead center by 10 degrees, 15 degrees. We got it. We got that. That will go good. I'm glad. Then you go, well, Mr. Romer, how do we tell the computer when to do it? How does it know? Well, advanced modern cars, they use a computer. There is timing marks on your wheel so you guys will know there are several ways the computer can see what the engine's doing. One is there will be a timing ring on the crankshaft, an actual tone ring on the crankshaft. The crankshaft will have a thing with the little notches, and one of the notches will be missing. Another company had this huge thing with a real spike on it. Some will have markings. Some will use camshafts. They'll put markings on a camshaft. You guys will hear things like camshaft angle sensors, right? So basically the computer's looking at where the camshaft is and go, oh, okay, combustion events coming up. I can see each of the camshaft. You can degree a camshaft. Let's just talk about a crankshaft, shall we? So as the camshaft spins around, the computer counts the teeth. 1, 2, 3, 4, 5, 6, all the way up to 270, right? And so as the computer sees tooth 268, 269, 270, 271, hey, wait a minute, 271. Could be a combustion event coming on. Wait, let me check my notes. The computer's going, let me check my notes. Here's my fuel air table. How many RPM are we doing right now? Oh, Kurt's got 5,000 RPM. Yeah, the pedal's halfway down. He wants us to be on the gas. Okay, so we've got load. We've got engine speed. It says that 3/4 of the way pushed down on the gas pedal at 5,000 RPM. Oh, the number is 263. Okay, or 273. Oh, 273 is 27 degrees advanced. So 271, 272, and finally, when the degree wheel hits 273, send the spark now. And the spark people go, aye, sir. Ding! And they send the spark through the system to the spark plug, where the spark goes blah, right? And ignites the mixture right at the proper point. And you go, well, Mr. Romer, they didn't have computers in 1968 when you were born. And I would go, you are correct. Well, not really. The ENIAC was built in the 1950s. The first computer was in the 50s, but it was the size of a warehouse. Anyways, you're right. Old-timey cars used a distributor cap, a rotor and distributor cap, which was just this. Rather than having a computer count the timing marks on a degree wheel on the crankshaft, they said, well, you know what we should do? We're going to give it its own ring and pinion gear set. So we're going to put a ring with the threads on the ring, right? Because it's gear now. We're going to put this gear wheel on the crankshaft, and we're going to attach to the crankshaft this metal rod with its own gear on the bottom that's pushed up against this round ring. So it's a ring and pinion, right? So that as this wheel goes, this shaft turns. And at the top of the shaft, we're going to have a little bar, almost like a pen. And if that pen sits on top of this shaft, as the crankshaft turns, the shaft will turn. And if the shaft turns in direct one-to-one relation with the crankshaft, the rotor spins. I want you guys to get this in your head. As the crankshaft goes around, the degree wheel turns, the cut geared ring or wheel is put onto that, and that spins. A shaft is connected to a pinion, and that's connected to that ring gear. That spins, just like a drive shaft into a universal, but stood up, right? That spins, and at the top of the spinning shaft is a little bar. It's about the size of half a pen. And that spins around too. Now you'll notice, and if you're paying attention, you'll go, oh, so at 10 degrees, that ring and pinion will have turned that little rotor 10 degrees. Here comes the fun part. Smart engineers said, well, wait a minute. If we put a cup underneath it and we attach all kinds of electrical things to it, and we energize that rotor and put a copper sheet on the top, and then we take a cap and we put it over it to cover it all up. So now the rotor spins in an enclosed area with a cap on top. We can take, this is how smart engineers are, we can take and drill holes down through the rotor at specific interval and places. We can fill that hole up with copper, because this has a copper leaf on top, like a little baby leaf spring, right? Attached down through the shaft to all those electronics on the plate that provide electricity to it, 12 volts into the plate, through the actuator arms and everything else down here, which then energizes this at specific points. So they put a cap on top of it, that holes are drilled out in the plastic cap and then filled with copper, right? So that at the top of the cap, there are a series of posts, and each of those posts has copper in it. A smart engineer said, you know what we can do? We can take electricity, put it into the shaft, into the dinner, that plate underneath with all the electronics. We can have electricity go to that plate, come up through that end of the shaft, up through that rotor where it has that copper leaf spring. And as it spins, in one-to-one relation with the engine, because remember, it's connected down through its solid shaft to the pinion, which then connects to the ring gear. So as the engine rotates once, the rotor rotates once. Guy says, you know what? We can attach wires to the top of that, to the spark plugs on each cylinder for the engine. And so a 4-cylinder car would have 4 holes on the top of its distributor cap filled with copper, and each of those would have a wire called a spark plug wire to go out to the spark plug, right? And so as the rotor inside spun around, and the copper that was in the rotor cap, when this rotor that's energized met and swept underneath the bottom of the hole that was drilled in the cap that's filled with copper, as it swept by, the electricity in the plate built up in a little coil pack would discharge through the rotor shaft, out through the rotor head, down along that copper leaf spring, out to the cap connecting point, that contact, right? Up through the wire and out to the spark plug, having an ignition event. So old-timey guys figured out how to attach a distributor shaft to a ring and pinion gear set off of the crankshaft, so that as the crankshaft rotated, the rotor would spin in perfect one-to-one time with the crankshaft. The smart kids would know that in a one-to-one, we dealt with what's known as a wasted spark scenario. That the cylinder would also get spark not during a timing event. Some rotations, it would fall when the exhaust gases were being pushed out. Creating a 2-to-1 was the natural progression from this. But initially, distributors were run on a wasted spark 1-to-1 configuration. Later distributor caps, when they started timing the distributor caps and setting up the distributor cap so there was only one way you can mate it so that you didn't get it on the flipped. You weren't just giving signal events for when the piston was in its clearance. In other words, it was pushing all of the exhaust gases out. You weren't wasting the spark and not getting a spark on a compressive event or when the piston's squeezing. So, all of this, Mr. Romer, an hour's worth of talking just to get to advanced mechanism. I had to tell all of you this so that you would understand, well, okay, so now we have a one-to-one relationship between the rotor and the distributor cap, sending electrical bursts of electricity out to the spark plug to ignite the mixture. We got all that, Mr. Romer. So how do you advance this system? And here comes the fun part. You would be actually able to take the housing of the distributor cap and the distributor housing and rotate it. Now, the rotor inside did not change its position. 0 is always 0 for the rotor connected directly to the crankshaft. That piece of copper along the top and this end part, if I set my engine at 0 degrees, top dead center for first piston, that rotor would always aim to a very specific spot. Now, what you can do is if you wanted to advance timing, you would loosen up the housing of your distributor and you would rotate it so that when it rotated, it's a 5-cylinder, right? It would rotate like this. Which one did you want it to point to? Or did you want it to point? So 0 degrees, number 1 piston, top dead center might look like that. But let's rotate the distributor 5 degrees advanced timing. So now, as the rotor spins, we're at 5 degrees. We've gone 5 degrees before top dead. This way. 5 degrees. No, it's this way, top dead center, right? So now, spark occurring after top dead center. So that's before top dead center. Right. Oh, right. We're 5 degrees before on the wheel. I'm just looking at the camera. I'm all getting backwards. So this is 5 degrees before top dead center. In other words, if I back up my crankshaft 5 degrees before top dead center, this copper slug representing cylinder 1 ignition event should be right on top of the rotor from the distributor housing. If I wanted to dial 10 degrees, so let's go back to 0. This is 5. This is 10 degrees before top dead center. Because remember, the crankshaft rotates this way as it sweeps through its ignition events. And you go, okay, Mr. Omer, we got it. Your finger's the slug on the distributor cap that sends electricity down to the spark plug. Your pen is the rotor, right? This is the cap, this is the rotor. And as the engine's spinning, it goes past and it meets up with this 10 degrees before top dead center, so that the combustion can perfectly meet the piston top at top dead center or a little after at maximum pressure to push down with maximum force. Are you going to be out there sitting in your engine bay twisting the distributor cap to give you 5 or 10 degrees before top dead center? How do we do this? Well, the first engines had a manual distributor. It was a lever used to put the distributor at predetermined advanced or retarded timing events. This was not good. The engineers said, we can do better. What changes in a car the faster you go? They said, well, RPMs. We can't use RPMs. What's a value that changes as the engine runs faster and faster? One guy from the back spoke up and he goes, well, the amount of vacuum in the intake plenum changes. And they go, what? What did he say? He said, the vacuum level changes. I said, what do you mean? He says, well, at engine idle, with the throttle plates closed, the engine's working, it's still trying to suck air in. And because the throttle plate's closed, a lot of air's not getting through. So there's a lot of vacuum. But when the throttle plate's open all the way at high RPM, there's no vacuum in the intake plenum. It's just flowing air down into the pistons. Now there's like a minuscule amount of vacuum, but that's brought about by a Venturi effect and flow rates. But with a closed throttle plate and the engine idling and still trying to suck air down with the pistons and the valves, you can get 30 inches of vacuum, 30 inches of mercury vacuum, and it goes down to like half of one, a third of one at wide open throttle. And they went, well, what about half throttle? And the scientist goes, well, half throttle is like 15 inches of mercury on a pressure jar. So half throttle's half the amount. Yep. What about a quarter? Yeah, you'll get about 8 or 7 inches of mercury at quarter throttle. What about 3/4 throttle? Well, or excuse me, at 1/4 throttle, you'll have like 20 inches of mercury. Half throttle's at 15. A quarter throttle is at like 5 or 6 inches of mercury. And then at full throttle, no vacuum, almost no vacuum at all. He said, we found it. Eureka! We found our way to modulate or change vacuum advance. So they wrote out some equations and they made some equipment. And what they ended up doing was they attached a small hose, little bitty air hose, from the intake where the vacuum changed, depending on how much vacuum your engine was developing in the intake manifold. And they attached it to the base of the plate on the distributor. And they put the plate on a clock spring. And now here comes the fun part. When there was a lot of vacuum in the engine because it was at idle, and that hose attached to the intake that had a lot of vacuum pressure in it at idle would suck the distributor cap into its 0 point, no advanced timing. Timing was set at 0. The engine was getting sparks, not before top dead center, but right at top dead center, because it's at idle, and then the engine's not chasing flame front. The combustion event is occurring perfectly at top dead center, where all the energy is getting pushed down onto the piston, because the piston's not moving fast at this point. 800 RPM. That piston's going up and down like my hand. Slow, right? But as you press the gas pedal and the throttle plate opens up, more and more gas gets, because your gas pedal, right? Gas pedal. More and more gas gets in. The throttle plate opens up, allowing more air in. RPM levels raise. There's less vacuum to be pulling on that spring, and so the vacuum lessens, and when it lessens, that little clock spring, that wound up clock spring, is allowed to decoil, because before it's all coiled tight, but since we've got a straw, we're sucking this one particular piece over towards our mouths. But once that level of vacuum lessens, it allows the spring to open up a little bit. And as it opens up, it rotates the distributor cap. And as it rotates the distributor cap, the timing of the ignition events goes into advance. And the distributor cap goes and turns to those points that offer advanced timing for different points. So at half throttle, half the amount of vacuum pulling against the clock spring can only have half power. And so the distributor is allowed to move into its halfway position, which could be 6 or 7 degrees top dead center, depending on the clock spring, depending on the vacuum points. There's a lot that goes into it, but that's basically what's happening. And at wide open throttle, there's no vacuum at all. That clock spring is allowed to open up to its biggest position, 20 degrees before top dead center. Now your engine has all the advance built into it because all the pressure's away and the vacuum's away, and it can stay as open as it wants, but its openness is its furthest most advance. And the engine's high RPM, right? 10,000 RPM, 20 degrees via vacuum. The clock spring was allowed to open it up, and the distributor is now spun at a point where, as the rotor comes up towards top dead center, it's really spun over, right? It's adjusted its way all the way over. So now the ignition event occurs at 20 degrees before top dead center. The vacuum, the distributor cap, the cap and rotor, and the rotating distributor assembly is all part of the advance mechanism and how to dial in advanced timing on old-timey engines. It's quite the feat, thinking about it, in what technologies they had back then. Now it's all computer driven. It's all solid state, microchips and bandwidth and microprocessors and RAM, random access memory, and programming and program languages, and it's its own level of sophistication and difficulty. But back then there was definitely a lot of mechanical ingenuity that went into it. That's really interesting. Also, not very efficient. Super inefficient. Horrible. Yeah. Advanced mechanism. Research it. Take a look. Get yourself some video animations. I don't have the ability to animate here. A lot of it has to be me taking you through the little steps so that you build up in your mind's eye what it does. Now that I've talked to you through this through an hour and 15 minutes of a video, I want you guys to do me a favor and go and look at old distributor systems for cars. Research distributor caps, distributors, and you'll see how the advanced mechanism works. How you tune a car by setting pre-advance. And then the advance on that works on top of it. Finding a degree wheel. What's top dead center? I want you guys to research that in Google and YouTube. YouTube it. I'm sure Donut Media's got something fun. I'll look it up myself and maybe I'll post it as part of this. But this represents a good amount, and I might even make a video for it. Modern cars don't go put a degree wheel on the crankshaft. They go right to the camshafts. The camshafts are phased direct one-to-one to ignition events. They don't have to wait for a compression event or an exhaust event on your crankshaft. Because remember, crankshafts go around twice. So they get half the resolution of a camshaft. A camshaft is direct one-to-one. This is the ignition event. This is the exhaust event. Okay. That's how camshafts have better what they call resolution. And you'll often find, like on modern cars, if there's a failure for the computer to correctly read the camshaft, it'll tell you that there's a camshaft sensor error, camshaft angle error. It's actually an error code. And I know Mr. King would be able to tell you what code it is. I don't. I just know that it's one of the codes that it gives off as a camshaft angle sensor error. The inability for your camshaft to be seen by the computer. And there's different means. There's magnetic, there's Hall, there's light sent, like one actually uses light beams. Not a laser, but it measures the amount of light that it catches. And when it gets to the detent or the tooth that isn't there, it reads as there's no light being reflected off the teeth. And that's one of the reasons, one of the ways that it gets seen. But I think most of them are magnetic pickups. They're degree wheels with like an itty micro sliver of either an imperfection in the steel or a little magnet piece of its own or an extra piece of metal so that the magnetic sensor reacts to that extra amount. That's what it is. And that extra amount's the 0 point so that it resets itself. But that's another conversation for another day. Today we're just talking about advanced mechanisms within the world of ignition events. That's it. A device used to trigger an earlier spark based on engine condition. Everybody, get ready to high five. Ready? 3, 2, 1, high five.